Okay, so today's lesson is going to be on solving quadratic equations graphically. This is going to seem quite similar to some stuff we've already done in the past. You probably already have a pretty good understanding how to do a lot of this. But anyway, let's get going. So today's plan is we're going to start with a quick review of standard and vertex form of quadratic functions. Then I'm going to introduce solving quadratic functions graphically. We'll do various problems and we'll get some practice. This is in your printed note booklet. It is, of course, under that same heading, solving quadratic equations graphically. And you can follow along as we go through. Here we go. All right, so starting with turning a vertex form quadratic into a standard form quadratic. So if we're going to convert from a vertex form quadratic to a standard form quadratic, we have to first tackle this binomial to a power of 2 here. What I mean by that is we need to expand it out. So I'm going to write this as f of x equals 4 times x plus 5, and then times another x plus 5. It's a very common mistake. People often try to bring this squared through by saying, oh, it's 4 times x squared plus 5 squared, but it doesn't work like that. We have to actually do the whole thing the long way, basically. Next thing you do is you can FOIL this through, but I think personally I might actually find it easier just to take this 4 and bring it in here first. What that's going to do is it's going to give me f of x equals 4 times x is 4x, plus 4 times 5 is 20, and that's still times x plus 5, and then minus 7. Then I will FOIL these two, because now it's just two binomials together. So I'll go 4x times x. This is going to give me f of x equals 4x squared. And then 4x times 5, that's going to be 20x. And then 20 times x right here, that's going to be another plus 20x. And then 20 times 5, well, that's going to be 100. And then, of course, we still have that minus 7 on the outside there, too. So this leaves us with f of x equals 4x squared plus 40x plus 100 minus 7 is 93. So that's just now a vertex form quadratic converted into a standard form quadratic. Really, we've kind of already done stuff like this before, but still good practice to see it go again. All right, the next step we're going to do is a standard form quadratic to a vertex form. Now, we've done a bunch of these. This is not new at all, but there's a bit of a trick to it. Remember, this standard form quadratic does not have the vertex listed in its actual form here, so you need to find the vertex using that little formula, x equals negative b over 2a. So negative b over 2a in this case is going to be negative 30, so that's going to be positive 30, over 2 times a, so 2 times 5. And of course, that's just going to be 30 divided by 10, so x is going to equal 3. But that's only one part of our vertex. The other part of our vertex is going to come by finding the y value of it, and that's just going to be take your x and plug it into your f of x. So we'll see f of x equals 5 times 3 squared minus 30 times 3 plus 12. This is just going to give us 5 times 3 squared is 5 times 9. Well, 5 times 9 is 45. Minus 30 times 3 is 90. And then plus 12. So 45 minus 90, that's going to be negative 45. Negative 45 plus 12, I'm pretty sure that's negative 33. So this is the x part of your vertex. This is the y part of your vertex. Vertex form always looked like y equals a times x minus h squared plus k. And remember from a while back that we talked that h and k is really just your vertex. So we know this is really your h, and this over here is your k. So that means we can just throw all these numbers in, and remember the a value is the same in both vertex form and standard form. So we'll say that y equals 5 times x minus h is 3, so x minus 3 squared. Don't forget the squared. A lot of people seem to leave that out. And then plus negative 33. So we might as well just say minus 33. So that right there, that is now in vertex form, with our vertex showing up directly in that quadratic equation right there. So we've done a few of those before. That certainly isn't anything new at all. But again, just like the last one, that is actually a really useful skill to have, because otherwise it can be a lot more difficult to actually communicate something that's useful. Because remember, standard form is really not that useful to us. Anyway, I'm blabbering. We're going to move on. So some more quick review here. Just how would one determine the max or min point on a quadratic? Just think about that for a second. How would you determine a max or a min point on a quadratic? Well, of course, hopefully what you're thinking is a max and a min point. That's just another way of saying a vertex, right? That's the whole point of what a vertex is. Remember, if you have a quadratic, it looks like this. Well, your vertex is your min. If it looked like this, then your vertex is your max. So in other words, you just need to find your vertex. So how would one determine that? Well, it depends on what form it's in. If it's in vertex form, you already have it. If it's in standard form, you have to do the x equals negative b over 2a. So I'm just going to simplify it down and just say find the vertex. Next one, how can you tell whether it's a max or a min? You guys were really good at this, actually, so I'm not going to spend a lot of time on it. But remember, if it's an upwards facing quadratic, like this one on the left that I drew up here, then it's going to be a min. Now, if it's a downwards facing quadratic, then it's going to be a max. So I guess we'll just say up becomes a min, and down becomes a max. And remember, to determine whether it's an upwards quadratic or a downwards quadratic, that has to do everything with the a value. If a is positive, then you have an upwards facing quadratic, but if a is negative, then you have a downward facing quadratic. So the last part of this is, what is the purpose of the a value? I kind of just told you half the purpose. So it determines whether it's up or down. That's one purpose, right? Whether it's positive or negative determines whether it's up or down. But then the other purpose of the a value is it acts as a vertical stretch. So it stretch it vertically about your x-axis, which just basically makes it either more thin or more wide if it wasn't as big of a stretch, right? That's what the a value does, not the biggest deal. All right, so quadratic equations. This is the name of chapter 4 here. In chapter 3, which was quadratic functions, we looked at quadratic functions in the form that is standard form on the left there, or vertex form on the right. Today, we're looking at quadratic equations. Now, there's just a subtle difference between the two. An equation is written as 0 equals ax squared plus bx plus c. Well, the only subtle difference is there we're actually looking at where f of x equals 0, or in other words, that's your y coordinate. So we're looking for where y is 0, or even more simply, where y is 0, what we're really looking for here is the x-intercepts. So when you have an equation, a quadratic equation where it's equal to 0, the solutions to this equation, in other words, the values of x that would make the whole thing equal to 0, those are your x-intercepts. So it's really important to understand that that's the focus of this new unit. We're not looking for the vertexes so much anymore. We're now more interested in finding those x-intercepts, right? Anyway, moving on. Now, one little thing I want to introduce before we go any further with this is the number of x-intercepts. So quadratics are kind of interesting. They can have different number of x-intercepts depending on what they look like. So I've got 3 pictures. They're kind of pixelated here, but 3 pictures that you can have a look at. The one on the left there shows that you clearly have 2 x-intercepts, right? So that's a total possibility. And 99% of the time, it seems, that's what we're really going to be looking for, right? Whoops, I just went backwards somehow. Whoops. Anyway, 99% of the time, that's what we're going to be looking at, because usually a quadratic does have 2 solutions. But there are certain situations where a quadratic only touches the x-axis once, right? So that'd be a situation where you only have 1 solution. But then even more rare than that, you sometimes have cases where it doesn't even touch it at all, like this one on the far right. There's no x-intercepts at all, so this quadratic actually has no solutions, or no x-intercepts. So a little note to the bottom is also important. X-intercepts, they have a million different names for some reason. They all mean the exact same thing. They're used just in like very slight different circumstances. You don't need to worry about it. But just keep in mind, x-intercepts are sometimes called solutions, as I've been saying a lot so far. Zeros, this is a favorite of your graphing calculator. Your graphing calculator calls them a 0. And then sometimes even roots. Roots, not really used as much, but they do come around. So if you ever see, oh, find the roots of this quadratic, it doesn't mean the square root. It means the solution, or in other words, the x-intercept. Okay? Anyway, moving on. So solving quadratic equations, there's actually 4 different ways, at least that we're going to learn in Math 20-1. The first way is graphing using a calculator. You're quite accustomed to this already. That's going to be the focus of today, but we've done it before. But that is just the one, like, really quick way for most people, at least, to solve the x-intercepts of a quadratic. It's just graphing in the calculator. The 3 other ways, though, are factoring, which is quite time-consuming, but it's also a really, really good method. We'll learn that another day. Vertex form, also known as the square root method. We'll talk about it another day, but again, I'm filming this a few days before I'm away, so there is a good chance we actually might have already covered that one. That was kind of something I would have covered just in lieu of doing this early. But anyway, the last one, however, number 4, which we will talk about later on, is called the quadratic formula. And that one is extremely powerful. That one will pretty much solve any quadratic you throw at it. But it's also important to know these three. And the reason being is these three can be quicker than the quadratic formula, but the quadratic formula basically gets it done no matter what, right? But again, we'll learn all four, but we're only going to look at that first method for today. All right, so solving quadratic graphically. To solve it graphically, you just have to follow these 4 steps. Step 1, ensure that one side of the equation, stuff that's actually on your piece of paper in front of you, is equal to 0. If it isn't already equal to 0, move everything over to one side, right? If it's all scrambled up, that's ridiculous, but move everything to one side to make one side equal to 0. Then type the non-zero side of your equation into y1 in your calculator. Then step 3, change your window so that you can see all of the x-intercepts. That part is honestly the toughest part of all. There's not really a rhyme or reason on how you do it. You just have to play around with your window settings and see where you can find it. I guess the only hint I can give you with that is it might help to find your vertex. And by the vertex, I literally just mean the x value of the vertex. You don't need the y value of your vertex. But if you find the x value of the vertex, generally speaking, is right in between your two x-intercepts. So if you got a vertex, let's say, and you found that x equaled 150, then that means you've got one x-intercept that's going to be more than 150 and one x-intercept that's going to be less than 150. So that might be a good starting point for you. But you don't have to do it by any means. You can just play around with the window until you find it. And for the most part, the ones we'll deal with, they're not going to be a huge mystery to find. Anyway, step 4, the actual finding of the x-intercept, press second, and then trace, and then go down to 0. And then just follow the instructions from before, the whole left bound, right bound thing. We've done this before. This is not super new, but really the one thing I really want to clarify this time around is ensure that one side of the equation is equal to 0. And you'll also need to make sure that your window has both the x-intercepts, or even if it's just one x-intercept, visible in that window. All right, so again, finding the zeros, press second, then trace, scroll down to 0 and press enter. Left bound just means use your arrows on your calculator to estimate just to the left of your x-intercept and then press enter. So on the screen, you'll see like this little dot that follows along your quadratic. Just keep pressing your left arrow key until it moves just to the left of it. Now I know from conversations we've had before, there's some confusion sometimes about what's the left bound, what's the right bound. I just rely on my arrows. So when I press my left arrow, I'll notice that my little dot on my quadratic is going to move left, left, left. And once it just passes that x-intercept, then I know that that's my left bound, right? Then it'll ask for a right bound. Use your arrows to estimate just to the right of your x-intercept. So in other words, press your right arrows until it goes just right of it. So that would be my right bound. And then it says guess. And what you usually should do is just, get as close to it as you possibly can and then press enter. And then that'll spit out what your x-intercept is, right? Now, if you were to do this other one, again, getting back to that left bound and right bound, playing around with the arrow keys will actually deduce that this one is to the left and this one up here is to the right, right? So in other words, don't go thinking that left is always above and right is always below. It all depends on the flow of your quadratic. Another way of thinking about it is if you drew a vertical line right here, notice that vertical line is to the left of this vertical line, right? That's pretty much all I can do to explain this one. But anyway, it just takes practice, right? And if you get something like an error that says bound error or something like that, then you know you've set your bounds incorrectly. All right, here we go. Here's an example. Find the root or roots of the following quadratic. So in other words, we need to do this graphically. You literally are just going to have to graph this, but I just want to spell something out for you before I get you to try this one on your own here. Remember, step number 1 from before is ensure that one side equals 0. Clearly, one side of this does not equal 0. We have to fix this. So I think the easiest way of doing this would just be to add 10 on both sides of this. So your quadratic you're going to get is negative x squared plus 3x plus 10 equals 0. So what I want you to do, we can pause the video in a second here, but what I want you to do is put this right here into y1 in your graphing calculator and see if you can find those roots. Anyway, you can pause the video here, give this a try. All right, I'm going to go over it. I don't have a graphing calculator on my screen to show you by any means, but I can tell you right now that if you put this in your graphing calculator, the solutions you should get are x equals -2. That's your one on the left. If you prefer to write that as a coordinate, you could write that as -2, 0. It's the same thing, like either one of these, it's fine. But then the other thing you could say for the other solution is x equals +5. Or again, if you prefer a coordinate, you can just say it's 5, 0. So those would be the solutions to that. That'd be the zeros, the x-intercepts, the roots, whatever you want to call them. Those are the answers to this question. All right, here's another one. I'm not going to spell this one out for you. I want you to give this a try. So punch in your graphing calculator and graph it. All right, so I'm going to go over this one now. Hopefully you caught the trick here. One side is not equal to 0, so what you have to do is you have to put that negative 16 onto the other side by adding 16 on both sides. That's going to give you x squared minus 8x plus 16 equals 0. And this right here is what you've got to throw into your graphing calculator. Now, something really interesting happens when you put this in your graphing calculator. The graph of this on a standard window likely looks something like this. All right, I'm just giving a rough sketch. It looks something like this. But what you'll notice is it only just touches your x-axis just once. So if you do your left-bound, right-bound thing, your left bound will be over here, and then your right bound would be over here, and then of course your guess right down here in the middle. But what you should get is only one x-intercept, and that's x equals 4. Or once again, if you prefer a coordinate, 4, 0, right? So this is one of those cases where you actually only have one x-intercept, which honestly is kind of nice. It saves you some trouble for punching in your calculator. Anyway, moving on to the next question. I want you to find the roots of this quadratic. So remember, get everything to one side, throw it into y1. You can pause the video here and give it a try. So this is my favorite question of them all, because hopefully you were able to see it. If you were to put everything on one side, you're going to see you have 3x squared minus 8x plus 7 equals 0. And then this part right here is what you throw into your graphing calculator. And if you put it into your graphing calculator, what you're going to notice is the graph looks something like this time. Well, notice now there are absolutely no x-intercepts, right? That means there's nothing more you can do with your graphing calculator. You put in your graphing calculator, you saw what the graph looks like, and you go, hey, what gives? There's no x-intercepts. Well, guess what? That's literally what you get it right. You just say no x-intercepts. Or if you say no roots or no solutions or whatever you want to call it. But the answer to this one is basically just no. There's no roots. There's nothing you can do here. All right, anyway, moving on to the next one. So something just kind of interesting I want to illustrate to you. I want you to consider this. 3x squared equals 12x minus 4. Does it matter if we move everything to the left side of the equation versus everything to the right side of the equation? Well, here's what you got to think about, right? Let's start by moving everything to the left side of the equation. So I'd have to minus 12x and add 4. That would give me 3x squared minus 12x plus 4 equals 0. Well, that's all well and good. You can graph that in your calculator if you want, or you can compare if I moved everything to the right side of the equation. And in this case, that probably is easier because you only got one thing over here. So if you just minus 3x squared on both sides, you're going to see 0 equals negative 3x squared. So weird 3, there you go, negative 3x squared plus 12x minus 4. So it's like everything's flip-flopped between the one on the left and the one on the right. But if you graph these in your calculator, is it going to matter to find the solutions? Well, you'd think it would, because this is an upwards facing quadratic and this is a downwards facing quadratic. But guess what? It actually doesn't matter. So even though one is upwards and the other one is downwards, the x-intercepts actually remain the same. So the answer to this is no, it doesn't matter. The x-intercepts actually don't move whatsoever. Now, I don't actually have a graph of this in front of me, so I don't even know what the vertex of this is. I mean, I guess I could calculate it, but I would assume that this one on the right probably looks something along the lines of this, I'm guessing. Again, I'm just completely freehanding this. I have no idea what it looks like. But let's say its x-intercepts are here and here. The one on the left is going to be an upwards facing quadratic. I can guarantee that it's going to have the same x-intercepts, but it's just going to be flipped around like this. So the x-intercepts, also known as solutions, also known as roots, they're not going to move. It's just with flipping this over to the other side of the equation, it just completely flips it upside down. That's all, right? But your solutions still remain at the exact same points that they were one way or another. So in other words, if you look back at some previous questions we did, if like maybe on this one you're like, oh, I moved everything to the right side and I still got no x-intercepts. Or if you looked at this other one, you're like, oh, I moved everything to the right side, but mine was flipped upside down, but I still got the same x-intercept. Well, that's the point. Your x-intercepts will not change. It's not that we're looking for a vertex in this case. This definitely would affect the vertex, don't get me wrong, but it won't affect the x-intercepts, right? Anyway, so that is actually everything. That was actually a decent lesson today. It was a little longer than I was hoping, but not too bad. So what I want you to do for practice is page 215, questions 2 to 8. If in a previous lesson I already gave you the chapter 4 homework assignment, you can start picking away at that too. I don't know which questions you'll be able to cover, and if I haven't given that to you, then you can just ignore that message. But either way, make sure you're getting some good practice at this, and talk to me later if you have any questions.